So it's my pleasure today to say welcome to Frank Wilczek. And he's coming to the Department of Physics of Stockholm University. And this is a kind of reception for him to the department, we could say. So you were installed as professor at the Stockholm University in late September in the City Hall. And you gave a short talk there. Maybe this is the longer version of the same thing. So it was in early 2015 we got the message that the VR had granted a 10 years contract to recruit Frank Wilczek to Stockholm. So we got 60 millions to recruit him to build up great activities during the coming 10 years. And of course our dean, Anders Karlhed, sitting down there, was very important in this process. So thanks to you for this. So this will be kind of introducing you locally here at Alba Nova, and I think you will talk about different aspects of what you would like to promote when being here. And this professorship was then came about by a calling procedure by the Vice Chancellor, and he started now the 1st of May 2016, half a year ago. So he will then be spending different periods during the year in Stockholm. And we are very happy to see the latest newsletter from the Stockholm University. You can see Frank saying, "I love Stockholm." We like that. Yeah. Jag älskar Stockholm. You speak Swedish, I understand. So now you have 4 affiliations. If you get an email from Frank, it says Stockholm University, it says Herman Fersbach Professor, MIT, Chief Scientist, Wilczek Quantum Center, Zhejiang University of Technology, Hangzhou, and it's Distinguished Origin Professor, Arizona State University. So you're a busy man. I mean, you have a very long CV, and I will not spend a lot of time to go through that, because we would like to listen to you instead. But let me just say a few things connecting to your visits to Stockholm. Of course, the first one was 2004, when you received the Nobel Prize, together with Gross and Pulitzer, for the discovery of asymptotic freedom in the theory of strong interaction. That was in 2004. And then in 2007, you were here as a Nordita visiting professor, spending, I think, a couple of months. Yeah. And then you presented the Oscar Klein Memorial Lecture in 2013 and got this Klein Medal. And last spring, 2015, you presented the Lise Meitner Distinguished Lecture. So you have been a close friend to us here, coming frequently. So now we are honored and proud to have you here as a colleague with us. And we expect a lot of changes for the future for you, inspiring us to new areas in research. And as we wrote in the advertisement, there will be a reception afterwards to celebrate your coming here. So it's time for you to present your talk, Augmenting Reality, Axions, Anions, and Entangled Histories.
Thank you very much. Thank you. Well, thank you for that lovely introduction, Sven, and good evening. It's 3:21, but I looked outside. It's a great pleasure to introduce myself here to those of you who may not know. And I'm going to be discussing in this lecture my current interests. Necessarily, the discussion will be superficial, but I'll be here, and I'll be very happy to talk with you further about the things that may intrigue you. There's a lot to cover, so without further ado, I'm going to just start talking about physics. So there will be 3 subjects: axions, anyons, and entangled histories. First is axions. Few aspects of experience are as striking as the asymmetry between the past and the future. If you run a movie of everyday life backwards, that's the operation of time reversal, it doesn't look like everyday life. You see this is something you don't see very often. Although if you looked at small little bits of that process, the laws of physics are obeyed. Things can spontaneously, if they have enough energy, they come together and come up to and make the building, and then at the end you found that the energy came from an explosion. But it doesn't look like everyday life at all. Things like that don't happen in everyday experience, and we're very familiar with the difference between the past and the future. We remember one and guess about the other. And yet, amazingly, time reversal symmetry was a notable property of the fundamental laws of physics for several centuries. Starting with Newtonian mechanics, which is based on accelerations, so it has two powers of time. If you change the sign, the law doesn't change. And continuing through general relativity and quantum electrodynamics. That situation raises two basic questions. One, a question about the foundations of statistical physics and the macroscopic description of the world, is how do we get from laws that are symmetric in time to appearances that are so very asymmetric? This is the arrow of time problem. It's a fascinating problem, but it's not the subject of this lecture. The problem that I want to focus on is a kind of why problem. Why are the fundamental laws symmetric? It's not necessary in the description of the world. This is a natural of everyday experience, and yet the laws seem to have this property. This is a naturality problem, if you will. As long as time reversal or T-symmetry appeared to be an exact fundamental feature of physical law, it was unclear that asking why would be fruitful. When you can keep asking why about anything, why, eventually you have to hit rock bottom. And the fact that the laws are the same forwards and backwards of time might have been rock bottom. I think that's the attitude that Newton and Maxwell, for example, had. But the issue became richer, more structured, and the question more unavoidable in 1964 when Cronin and Fitch, together with Christensen and Turley, discovered a subtle effect in K-meson decays that slightly violates time reversal symmetry. Okay. For Sticklers, it was actually CP symmetry that they found a violation of, but CPT is kind of sacred, so it's morally equivalent to time reversal violation. In 1973, building on the emerging core theories or standard model of strong and electroweak interactions, Kobayashi and Masukawa made a major advance on this why question. In the context of the core theories or standard model, we discover that quantum mechanics, relativity, and gauge symmetry, the specific gauge symmetry of the fundamental particles, combine to greatly constrain the possible interactions of physics. The things that are consistent with those general principles are very restricted. And Kobayashi and Masukawa showed that if you have two generations of quarks, which was what was known at the time, no time reversal violation can arise. All the allowed interactions by those sacred principles also happen to respect time reversal symmetry. While for 3 generations, you can sneak in a little time reversal violation and you get a one-parameter theory of that effect. There's an asterisk here which will be all important. It'll appear I'll explicate it momentarily. So the KM work was a brilliant success. It was certified by the Swedish Academy recently. A third generation was subsequently discovered as they required to bring in T violation. These were the B and D T quarks and also the tau leptons. And their one-parameter theory predicted and now successfully describes many reactions and decays that weren't known at the time, a host of T-violating effects in weak decays of heavy quarks. And yet, with more profound understanding of quantum field theory, people realized that the KM explanation of approximate T-symmetry has a big loophole. Indeed, there's another possible T-violating interaction that they didn't take into account. So actually, there's a two-parameter theory. They had just inadvertently set one of the parameters equal to 0. The new interaction is a very subtle one. It's an interaction among color gluons, which is profoundly quantum mechanical and does not show up in any order of perturbation theory. So we say it's non-perturbative. If you don't know what that means, it means it's subtle. This is the form of this interaction. You can write it down. It's an interaction among the colored gluons, which are very similar in mathematical structure to photons, except that there are 8 of them instead of just one photon, and they respond to the color charges of the strong interaction rather than electromagnetic charges. But you can still recognize that there are electric fields and magnetic fields of these colored gluons. And this is the form of the new interaction, written in terms of the color gluon electric and magnetic field. It's an E dot B interaction. And it's parametrized. Its coefficient is written as this parameter theta. There's also a strong coupling constant there. Okay, and this is the relativistic notation. So this is consistent with all general principles and yet violates time reversal symmetry. So it undoes, or at least exposes, a loose end in the Kobayashi-Maskawa work. The theta term changes sign under T. You could tell that from the epsilon symbol in the relativistic notation, which has 1 time index, or you can tell it from the E dot B form, because electric fields don't change sign on a time reversal, but magnetic fields do. So if the coefficient is not 0, we have a new source of T-symmetry violation. And the theta term is especially dangerous to have because it feeds directly into the structure of nucleons. Nucleons are held together by gluons, and if the gluons have this kind of asymmetry in their interactions, it infects the structure of nucleons in such a way that it induces an electric dipole moment. Let me show that in a picture. We're all very familiar with magnetic dipole moments associated with spinning objects, such as the Earth, but also neutrons, electrons, and other elementary particles have little magnetic fields, dipole fields, associated with their direction of spin. One can also imagine, why not, electric fields that are dipole, with respect to all general principles of relativity and so forth, but not time reversal symmetry. Fundamental dipole moments, both magnetic and electric, are among the most accurately measured quantities in physics. You can really do a very good job on them experimentally. Magnetic dipole moments give precision tests of quantum electrodynamics. This is one of the places where quantum electrodynamics gets tested to better than parts per billion in its predictions, and constrain possible contributions from beyond the standard model. On the other hand, no non-vanishing fundamental electron dipole moment has ever been detected. neither for electrons, muons, neutrons, protons, nor for a smorgasbord of sensitive nuclei, atoms, and molecules. The bounds are extraordinarily small. Let me show you some of the most important ones. So the electric dipole moment of the tellurium, or is it tantalum? One of those. 205 nucleus is 9 times 10 to the minus 25 e centimeters. I'll skip to the neutron. It's less than 6 times 10 to the minus 26 e centimeters. Now, in case that number doesn't mean anything to you, the neutron size, whether measured by its Compton wavelength or its geometric size, its charge radius, is about 10 to the minus 14 centimeters. So we're talking about limits on the redistribution of electric charge within a neutron in response to its spinning, which are at less than the part per billion level, much less. So in terms of that theta parameter, which would directly induce electric dipole moments, we're led to conclude that the absolute value of theta is less than 10 to the minus 10th. That is a naturality problem. If you have no good explanation of why it shouldn't be of order unity, and in fact it's 10 to the minus 10th, that's quite a coincidence. Is it a coincidence? I think not. Over the past 40 years, there have been several attempts to address this so-called coincidence, or apparent coincidence, or not coincidence, but only one has stood the test of time. It involves introducing a new fundamental principle, a new symmetry into our core theories called Peccei-Quinn symmetry, after the physicists who first thought about it, which is spontaneously broken. Now, an accurate description of what this symmetry is and its breaking would require a long technical exposition, and I'm not going to do that in this colloquium. But very roughly speaking, what the outcome of the theory is that one promotes the numerical parameter theta, which was just a coupling constant, a parameter of fundamental physics, in the standard model as it comes. After you supplement things with this extra symmetry, the theta parameter becomes a dynamical field, something that depends on space and time, and has dynamical equations. And it turns out that this dynamical field can, and if you set things up in a reasonably simple way, it wants to relax to zero. So dynamics favors close to a zero value for this parameter. And that explains the smallness of the observed theta. Now, the most striking consequence of this proposal is the emergence of a new kind of particle. This gives us something to chew on, to shoot at, to take these ideas from virtual reality into augmented reality, which I named it the axion in homage to a laundry detergent. People doubt this story, but I have evidence. When I was a teenager, and I wasn't much more than a teenager when I developed this theory, that matter, I'm not that much more of a teenager than a teenager. Yeah. I had noticed in the supermarket a laundry detergent named Axion. And I said, gee, that sounds like a particle. And if I ever get the chance, I'm going to name a particle after that laundry detergent. And a few years later, I got the chance, and I said, well, you know, it's erasing a stain from the standard model. Why not? And I managed to sneak it past the editors of Physical Review Letters, and that's stuck. So axions are basically the quanta of this theta of x and t field. So they're very close to the foundation of this solution of the T problem. The effective theory governing the mass and interactions of axions contains one main parameter, which is a mass scale, usually called F. Phenomenologically, it's a very large mass scale, greater than 10 to the 9th proton masses. There are also, to be honest, a handful of discrete parameters that affect details of the axions coupling to matter. But to a first approximation, the key facts about axions are that they're very, very light scalar particles. The mass is 100 MeV squared divided by F, but F, remember, is very large. The 100 MeV comes from a QCD scale. And if F is a kind of typical value, 10 to the 12th GeV, the mass of the axion is 10 to the minus 5 electron volts, which is smaller than the mass of any other particle that has non-zero mass, except possibly for one of the neutrinos. And axion couplings are proportional to 1 divided by F. This means, since F is very, very large by normal particle physics standards, axions interact very feebly with ordinary matter and with each other. Since the theory is reasonably definite in terms of this one parameter F, one can calculate the predicted cosmological genesis and evolution of axions through the Big Bang. And one predicts in this way the presence of an axion background, very roughly analogous to the microwave photon background, which is also produced in the early universe through other interactions in equilibrium at high temperature, but different in crucial respects. First of all, it's not a black body distribution of photons. In fact, it's or at least starts out as a Bose condensate, very, very cold, of feebly interacting non-relativistic particles. That's a dramatic way of talking about a classical scalar field. The gravitational influence of the axion background is stronger, and its non-gravitational interactions are much weaker, much feebler. This means, if you put it all together, and if you analyze it also more carefully quantitatively, that the axion background, this relic of the early universe, is predicted to have properties consistent with the observed properties of what the astronomers have discovered, the so-called dark matter. So the bottom line, when you put together the limits, the properties, and the constraints, is that if axions exist at all, they must contribute significantly to the dark matter. And since they have to be a lot of it, why not speculate that they're all of it, especially since nobody's found the other stuff, other candidates. So in recent years, several clever strategies for axion searches have emerged. And this, I think, is very exciting, and one of the things I hope we can explore and develop further in coming months. I should mention that there's going to be an axion workshop, an axion dark matter workshop here in a little over a week. So here's one method. Axions in the presence of a magnetic field can convert into photons, which then you can see with your eyeball. So that's that experiment. It's a little more sophisticated. The I told you that the theta term would induce an electric dipole moment. That means a residual theta field that's changing, gives you a changing electric dipole moment, very small, but a very small changing electric dipole moment. And this is something you can try to detect through very clever magnetic resonance techniques. I won't describe them in detail here. Another thing is that axions in magnetic fields produce electric currents. I'll show you that in equations a little later, well, momentarily. And you can try to detect the magnetic field set up by the axion background. This is the so-called abracadabra experiment. Another thing is that axions can form, they're very, very light particles, so their Compton wavelength is very, very large. And if their Compton wavelength is large enough, they fit the size of a black hole, and they can make black hole atmospheres. So as we learn more about black holes through gravitational radiation and other probes astronomically, we can see if in fact they have no hair or axion hair, which would change their properties quite a bit. Finally, there's some of this story that's already borne experimental fruit. In condensed matter systems, one finds emergent axions, of course with very different parameters, but the same equations. In fact, the surface of a topological insulator can be considered as a gas of emergent axions. That is, it obeys the same equations as a gas of emergent axions. In this case, it's not the color electromagnetic fields, but the just plain old electromagnetic fields that are significant. And let me show you how the equations you get from this Lagrangian. They're very simple and canonical looking equations. In the context of condensed matter, you also predict a quantized value for this kappa parameter. And we have many interesting effects. It says a magnetic field will induce charge on the surface of such a material. This is the effect that I told you the abracadabra experiment is looking for. A time-dependent axion field acts as a current that sources other magnetic fields. And this is a dramatic transport property of the topological insulators or other materials that have this kind of emergent axion. An electric field induces a transverse current. And I was thrilled to see a few months ago that experiments demonstrate this effect, the quantized Faraday and Kerr rotation. So if you shine light through these surfaces, there's a parity and time reversal violating effect that the plane of rotation rotates a little bit. When it goes through, that's called the Faraday effect. When it's reflected, that's called the Carr effect, not Kerr. That's very important. Here is an important part of their abstract. So it provides evidence for the long-sought axion electrodynamics and topological magnetoelectric effect. And very nicely, you can even check the quantization, which is a very unusual thing in condensed matter, to see quantized properties emerging. It's like in the Josephson effect or the quantum Hall effect. There aren't very many examples like that. And this is another one. They find that they get a value which is reasonably close to the predicted or the known fine structure constant. You could work harder and do better, presumably, but that's how should I say, measuring how much little rotations, how polarizations have rotated is not as easy as measuring voltages, so one shouldn't expect comparable accuracy. Okay, so that's axions. Now let me move on to anyons. In 2+1 dimensions, quantum kinematics allows new possibilities for quantum statistics, besides bosons and fermions. There are several perspectives on this phenomena that give different kinds of insights into it. One is that in 2+1 dimensions, if you think about the world lines, we can think of them as strands in a three-dimensional space. And in 2+1 and in 3 dimensions, strands can get tangled up. This is called braiding theory and is the theory behind why people can braid their hair and it doesn't fall apart. In higher dimensions, braids can always be undone continuously, it turns out. I'll let you do that thought experiment. And so there's no topological distinction that records how much one path has wound around another. And a result of that is that the only way to have paths that are, to have different ways that to get from the same kind of initial state to a final state that are sensitive to the topology of paths is if you change two identical particles' positions, if you do permutations. And that gives you bosons and fermions. But in 2 dimensions, it's much more general. You can do all kinds of tangling up and introduce topological interactions. So that's one way. Another way, this is the way I first got into this, is that if you believe in a spin statistics theorem and realize that in 2 dimensions, the angular momentum algebra is trivial. It's just, it's abelian, there's no non-trivial commutator, there's nothing to fix the normalization. So you can have a fractional offset in the quantization, and you would expect, therefore, fractional statistics. And the most profound way, and the most useful, is the perspective of discrete gauge theory. That's to notice that in 2 dimensions, tubes of flux degenerate into points. So they can be flux can be associated with particles. Magnetic flux can be associated with particles, which means that you can have Aharonov-Bohm effects, that is, effects that occur without any magnetic field, but just with potentials that give quantum mechanical phases as one particle goes around another. And this construction supports either abelian or non-abelian interactions and also doesn't require that the particles be identical. You can have funny quantum phases between different kinds of particles. So particles that partake of these new possibilities are called anyons. I introduced that name to suggest anything goes in 2 dimensions. In 3 dimensions or more, it turns out there are bosons and fermions are basically the only consistent possibilities. But in condensed matter systems, 2-dimensional systems, 2 dimensions are very common. You can freeze out motion in the 3rd dimension. In fact, of course, most of microelectronics is based on 2-dimensional chips. So anyons arise in nature, not only as these mathematical possibilities in virtual reality, but as in augmented reality, in our conception of the world, as elementary excitations or quasi-particles in highly entangled quantum states of matter. They are, in fact, defects in the pattern of entanglement. So you can think of the different spins, say, in a system having an entangled wave function. And if you have defects in the pattern of the entanglement, if there's a non-trivial pattern in the ground state, you can have defects in it, and those turn out, if you imagine rotating one defect around another, things can get even more tangled up, and that would give you additional phases or even non-abelian effects. So there's a memory of the motion that gets imprinted on the wave function, and that's the source of anyon behavior in the world. Now, typically, the effect introduced by an electron is larger than the most basic defect in these states. Bigger, it's more than the quantum of disturbance. And therefore, electrons can fission into several of the more basic defects, which are anyons, logically, because they have fractions of the electron's statistics of its effect on the wave function as you move them around. For the electrons, this can be a shattering experience. That's a joke. But here's a picture of it. The electron is getting pierced by a flux tube. But the offspring that result from this process emerge with brilliant new powers. Now they have memories, and it may be possible to exploit the memory abilities of anyons to do useful quantum information processing, and that's a very lively, interesting subject that I hope I've intrigued you with. Bert Halperin recently in his Lisa Meitner lecture here talked quite a bit about this. Quasi-particles in many fractional quantum Hall effect states are firmly predicted to be anyons. There's also good numerical evidence for it, and many experimental confirmations of the underlying theory. So there's no doubt among theorists that quasi-particles in many, many fractional quantum Hall states are anyons of different kinds. But direct experimental tests have proved difficult because the anyons are usually electrically charged. They are all kinds of practical problems, which I'll just flash. It may be possible to overcome them. They're practical, not fundamental, and people are working hard to try to overcome them. And there are other ways of accessing some of the same behavior. But here, I want to discuss a new, radically different possibility that has gotten me excited recently. So there's a lot more to say about anyons, but I have to be selective. And, but I just want to whet your appetite, so to speak. Okay. So it is widely expected, based on solvable models and numerical work, that several two-dimensional insulators should exhibit what are called spin-liquid phases. Spin-liquid is not a well-defined concept presently. Different people mean different things by it. The basic idea is that if you have a system that has electrons that don't move, but they can still have spin degrees of freedom, so these spins can move around. If the spins are frozen, like in a ferromagnet or an antiferromagnetic, that's a solid. They don't move. If you're at high temperatures and they move freely, that's a spin gas. And in between, if there are other phases that you don't know how to talk about, that's spin liquids. That's the rough definition. The precise definition is a little less vague, but as I said, not universally agreed upon. But the qualitative features include formation of a gap in the energy spectrum, although some people also talk about gapless spin liquids, high degrees of entanglement, and absence of a local order parameter. So phases that have structure that's quantum mechanical, therefore not visible as in ferromagnets or antiferromagnets, but you can tell something is going on because there are phase transitions and maybe some other subtle signals. Several candidate spin liquids support anionic excitations. This is known from numerical work and theory. That feature provides, in principle, an exotically beautiful signature of the phase. You just look at the material and see if it has anyons. But how do you do that? That's been very problematic in the quantum Hall effect, as I mentioned. But in spin liquids, we have a big advantage that the anyons are electrically neutral, so all those problems I mentioned don't really come up. And I think there's a quite specific, beautiful thing that one can isolate that will nail this. The orbital angular momentum associated with a new channel, if you start to produce new kinds of anyon-anti-anyon pairs, has a direct quantitative or other pairs of excitations with anyonic properties, has a direct quantitative effect on the near threshold behavior. This is simple, basic quantum mechanics going back to Eugene Wigner and nuclear physics. If you open up a new channel, so you barely have enough energy to produce these new kinds of particles in a collision, centrifugal barriers can thin out the wave function. You have very, very little momentum. The wave function is very spread out, and centrifugal barriers really spread it out. So they introduce a suppression near the origin, and that shows up directly in the behavior of the cross-section near threshold. So I'll just give you a qualitative idea. If you have fermions, there's a suppression because the minimum angular momentum you can have for two identical fermions is 1. For bosons, there's no such suppression, so the cross-section sets right in. You have symmetric wave functions, no suppression. 0 angular momentum is allowed. If there's a hardcore repulsion, you get a suppression right at 0 momentum, but it shoots back up. If you have particles that have half the statistics of an electron, so-called semions, so when you move one around the other, you get all the way, you get a minus sign, not just halfway. Then the allowed angular momentum is half integer, and you get in-between behavior. And experimentalists, I think, should be able to tell the difference among these things. And that will be a very direct signature. So one can aspire to see these effects in neutron scattering and also in point contact tunneling. I expect that the threshold spectroscopy of quantum statistics that this indicates will evolve rapidly from a demonstration of the existence of anyons to a tool for figuring out the behavior of these spin liquids and distinguishing one from another. Okay, so much for anyons. Now I'd like to talk about entangled histories. Experimental physicists are achieving new levels of control over the production and manipulation of entanglement. Much of this effort is inspired by the vision of quantum computing, but quantum computing is very difficult. It's going to be a long time, probably, before we have general purpose, useful quantum computers. However, a lot of work and a lot of money is going into this. New capabilities are being discovered along the way, and it could be fruitful to consider what other benefits we can get from these new abilities to manipulate quantum variables very delicately. So in that spirit, I'd like to revisit some very basic aspects of quantum theory and measurement. This will turn out to lead us to an enriched concept of what history means in quantum theory. So, from the perspective of quantum theory, interference arises from the possibility of getting to the same final state through several distinct paths. If that's possible, then according to the rules of quantum mechanics, you're supposed to add the amplitudes and then square, as opposed to just adding the separate probabilities, which are the squares of the amplitude. So I'll insult your sophistication by actually showing the equation. So the total probability is not the sum of the probabilities if the processes can both contribute with the same initial and final states. But for interference to occur, the final state of the whole universe, including measuring devices and the external world, must be consistent with either of the two contributing processes having occurred. And this, I think, for a long time has blocked people thinking about measuring histories in quantum mechanics, because if you want to measure interference, it's crucial to maintain or create ambiguity among different paths. I call this strategic ignorance. And to get two histories to interfere, we need to make sure the final state of the world, including the final state of the measuring apparatus, does not allow us to distinguish which happened. But if we hope to measure observables, that basic requirement that the different possibilities can't be distinguishable runs into tension with the idea that measurement disturbs or collapses the wave function of the system being observed. If it collapses the wave function when you make a measurement, then that definitely affects subsequent measurements, and you don't get histories, you just get the state at one time. So to get around this difficulty, we can correlate auxiliary bits with the system's sequence of states without disturbing its evolution uncontrollably. And this way, we can monitor but not measure the system's behavior. And then later, if we want to actually make a measurement, we can operate on the auxiliary bits with great flexibility. Let me show you an example, because these words are very abstract. So let's look at the classic two-slit experiment. And we imagine monitor bits, one behind each of the two slits, which are going to monitor but not measure where the photon went in the following way. They're set to down initially, and then if a photon comes through that slit, they flip to up. Now, that's not a measurement. It can be a unitary operation. It's the kind of thing that people in quantum computing call a C-naught operation, and is a very simple gate compared to what you need to do full-scale quantum computing. So here's the kind of monitoring. If you start with down and the photon goes through, it switches to up. If you start with down, the photon doesn't go through, it stays down. This can be extended to a unitary operator if you have also these things. And that makes what's called a controlled knot. Okay, you flip the spin if and only if the control bit is a yes. And here's a picture of it. Now, so we have, I'm sorry, go back to the picture just for definition purposes. So we have a monitor bit M1 up here and M2 down here. So if we measure the Z spin of M1 after this process, we learn which slit the particle went through, and there's no interference. We get D1 squared or D2 squared, depending on whether the spin was up or down. However, if we measure the total spin of M1 plus M2, it's quite different. When spin 1 appears, that's the total spin. That means we're in the symmetric state, and we get interference with D1 plus D2 squared. If spin 0 appears, we're in the anti-symmetric state, and D1 minus D2 squared appears. We can also consider more involved measurements, of course. We can shift the relative phase, and so we don't have to measure either Z spin or total spin. We can measure all kinds of things. We can also do things in the opposite order. We can measure the position where the photon lands before investigating those monitor bits and make predictions about what the monitor bits are likely to do. We can compute their density matrix. I'll leave it as an exercise for you in Bayesian statistics to figure out the density matrix given that gives those results. There it is. Okay, so to me, this gives a very nice perspective and explication of the foundational strangeness of quantum mechanics, that you can change change in a certain sense the behavior of what the electrons are doing based on what you do to the spins later, or vice versa. Now, we can apply the same procedure conceptually to monitor aspects of a system's behavior at different times. That is its history. If the top slit was one time and the bottom slit was another time, turn it on its side. That's the idea. So, if we consider, for instance, something as simple as a spin 1/2 particle, we can monitor but not measure chosen components of its spin at several times, and later make measurements on the monitor bits to get information about what happened. Let's see how this works concretely. I will, in view of the time, I will forego the definitions such as they are and go right to an example. So suppose we want to measure two formal objects. At this point, it would be hubris to call them observables because haven't told you how to observe them, but I will. And they are of the form you measure you have an operator at some time t2 and an operator at some time t1, and you want to apply that to the system. So these are historical or temporal observables because they depend on the properties at two different times. And those operators commute, even though at the separate times the things don't commute. The sigmas anti-commute, sigma 2 and sigma 1 at time t2 anti-commute, as do sigma 1 and sigma 3 at time t1, but the product of both of them commute, so you can measure them jointly if they really are applied as coherent objects. And you can figure out what their eigenhistory is, what it is you measure if you measure, say, that the result of measuring both of these is 1. That's the eigenvalue you get. And if you do that, you find that the history that corresponds to measuring plus for both these variables, they can obviously be either plus or minus because they square to 1. If you measure plus for both of them, that corresponds to this history. So it says either at time t1 you had spin up and then it stayed up, or you had spin up and it spin down with equal weight, or with weight I you have these kinds of flippings. This is an entangled history. It tells us what we know about the state of the world, or what happened, I should say, after we measure plus plus on those auxiliary bits, on those monitor bits. And it's a remarkable object, despite its simplicity. You can compute with it, but I'm not going to belabor that in view of the time. Actually I will. I'll do it. Just won't spend a lot of time on it, but I want to say that you can calculate, given an initial spin that you don't disturb it, that could be in any direction, and you don't disturb its dynamics, but just monitor it, and later measure what its possible histories are, you can measure the probabilities that different historical patterns occurred. So it's not just talk, it's not just baloney, it's not just interpretation of quantum mechanics. This is something you can actually concretely calculate with and test if you can measure these kinds of observables. So how would you go about measuring observables like A and B? The key is to set up it's very much like the two-slit experiment turned on its side, as I anticipated. That's why I told you about it. The key is to set up appropriate monitor bits and measure them judiciously. So to measure A, we set up a monitor bit for spin in the x direction at time t1, which is sigma x, and a monitor bit in the y direction at time t2, and then we measure neither one of those, but only the joint product, which in computerese is a not XOR. Okay, if both of them are up, it's 1, or if both of them down, it's 1. But if one is up and one is down, it's 0. -1 actually. And similarly to measure B, we do a similar kind of thing with the appropriate changes of direction. So that's how you measure those things. They are very concrete procedures. They do rely on being able to construct these sophisticated quantum gates, but if you have that ability, it's simple and straightforward. So in general, the eigenstates of temporal observables are entangled histories, as we saw already in that simple example, and therefore, when we measure the value of such observables, we often discover facts about the past of our system that can't be summarized, can't be captured by saying that it had a specific temporal sequence of properties or states. It has to have these kinds of entangled histories where different things might have happened at intermediate times that can't be just a product of states. Rather, what we infer is that it had a parallel evolution through several distinct sequences of properties. Or, to put it more dramatically, several distinct histories or worlds diverged but later came together. So entangled histories, as far as I'm concerned, are a precise, tangible, mathematical reflection of the intuitive many worlds interpretation of quantum theory. They have math behind them and experiments and protocols. So to make temporal entanglement observable as a practical matter, we should focus on very small worlds that haven't diverged very much, and then make them interfere so that you can show that they both existed simultaneously. We can do that using small numbers of monitor bits, as I sketched above. Or the way I'd like to put it is we can nurture Schrodinger kittens short of Schrodinger cats. And Schrodinger kittens are much cuter, they're more fun, and more manageable, and you can actually get them to do what you want. Okay, so let me make a conclusion. I hope I've intrigued you with some of these ideas. And conclusion I certainly feel justified in drawing is that creative physics allows us to get beyond everyday reality. We get to consider very, very interesting ideas about fundamentals, about the whole universe. It's really fun to entertain such thoughts, to entertain virtual realities that go beyond everyday reality. But to me, it takes on a different level, and I see much of my mission in life as going from virtual reality to augmented reality, to take those ideas into things that you actually can and do observe. So thank you very much, and hi. Okay. Okay.
So we have time for questions. Who would like to start? Then I warm up.
No,
Oh,
yeah.
okay, very good.
What is your current perspective on the possible role of anyons in high-temperature superconductivity?
Well, they were originally they were originally introduced on their own, but there was thought to be a possible application to the cuprate superconductors when very little was known about the cuprate superconductors. I think we can say with complete confidence that the cuprate superconductors are not described by the theory called anyon superconductivity. But I don't think that's the end of the story. Just a few weeks ago, I learned that experimentalists in cold atom physics are trying to set up the Hamiltonians that were used in the theory of anyon superconductors and realize them in cold atom systems. And if they do that, they will, in fact, observe anyon superconductivity. So we'll see. Yeah. It wasn't entirely wasted effort, I hope.
Yes?
Experiments on entangled histories.
What's that?
Any experiments on entangled histories?
Well, it's the mature version of this is not yet in print, so not really. There are some. There is an experiment that does a version of entangled histories using optics. That's kind of clumsy, but is used to illustrate the principles. So there is an experiment, but not quite an ideal illustration of this dynamics. But I don't think these experiments are terribly difficult once you know what you're doing, and would be great fun. I think even the two-slit experiment would take that very familiar phenomenon into interesting directions. You know, make it much more dramatic, the different possibilities, because you can choose whether to make them interfere or not later. You know, and see that what you measure for the spins much later affects what happened to the electron. Very cool. Okay.
Bengt?
Would you dare to comment on the philosophical problems that the successful experiments of entangled histories might raise?
Well, they're not experimental problems. I mean, not philosophical problems. They're philosophical insights. That's the way the world works. And well, let me make a general comment. Okay, I can't just leave it at that, I guess. People talk about many worlds, interpretation, and things like that very loosely. Okay, they talk about reality, the reality of these many worlds. But you know, some things are more real than others, I guess. Some things that are very remote from any observational consequence, those are virtual reality. And that's fine. Virtual reality is great fun. But it's not the same as augmented reality, where you actually get to sense it and observe it and interact with it. And to me, augmented reality is special. So if you like many worlds as a virtual reality concept and like to spring them, that can enrich your experience of existence. That's fine. But it's a separate thing from pointing out concrete experiments and measurements that are illuminated by this concept of entangled histories, which to me is the mathematically precise thing that many worlds is trying to capture. Yeah. Yeah.
Can I ask you, what would you go back and say to Maxwell and Newton?
Yes.
As a resume of your talk about T reversibility that they would understand?
Well, you could point to the equations, F equals ma, and as long as F obeys very general conditions that Newton had in his law of gravity and many other things that he thought about, that they depend only on positions, for instance, then the equation is time reversal invariant. If you change t to minus t, you get exactly the same equation. So if you take a configuration and run it, or reverse all the velocities and run it, and then reverse the velocities, run it backwards, you get what you started with. So that's a very remarkable property that was in the laws. And similarly, the laws of electromagnetics are like that. It's more subtle, which makes it more interesting. Because in Maxwell's equations, if you want to display the time reversal symmetry, well, there are two things, but let me comment on the first. First, at the level of the cleaned up Maxwell equations, with just E's and B's and no H's or conductivities and so forth, then you have to change the sign of the current and not change the sign of the charge, and change the sign of the magnetic field, but not the electric field. But if you do those things and change the sign of time, the content of the equations doesn't change. So that's a very non-trivial property of the Maxwell equations. When you do put in phenomenological effects like finite conductivity, it's not time reversal symmetry anymore. And I don't know, I haven't seen it explicitly in Maxwell's writings, but clearly he was very aware of the fact that conductivity is associated with dissipative processes, is associated with things that are maybe not so fundamental. So there was an instinctive, at least, understanding of time reversal symmetry, although I don't know that he brought it out explicitly. I would love to be corrected on that, but I'm somewhat of a student of Maxwell. I've never seen it Okay, and of course, general relativity also allows T goes to minus T, quantum electrodynamics. So it wasn't, and there were consequences derived in atomic physics, especially by Eugene Wigner. Eugene Wigner was a real hero of understanding symmetry in quantum mechanics that were verified. Absence of electric dipole moments in nuclei, he pointed out, I believe, was a consequence. But, well, I'm not sure where I'm going with this, but yeah, it's an interesting subject. It's been very fruitful, as of course, in a previous incarnation, the study of parity symmetry, spatial parity, as opposed to time parity, and its breaking proved to be a major wedge into getting fundamental understanding of the weak interactions, and in fact, of all interactions. So studying these symmetries and their breaking has been quite fruitful, and I think will continue to be. At least one more big episode.
Yes, Lars?
Well, since we're looking for things to do, interesting stuff, it looked like, for instance, this abracadabra contraction was rather small. So this is kind of tabletop experiment, more or less, or not?
Well, if you have a big enough table, no. They'll be here and describing it, but I think it's like 10 meters. No, it's big. It's 10 meters. Well, the bigger the better, I guess. And so you have to balance practicality versus sensitivity. So it's also a matter of what they can get people to pay for. So, yes.
We have many numbers in physics that are kind of unnaturally small.
Yes.
The ratio of the electron mass is squared and so on.
Yes.
That are much sort of worse than the 10 to the minus 10 you were using.
Not many are worse than 10 to the minus 10, I don't.
Because the cosmological constant.
The cosmological constant is, yes. That's right.
Why do we care about that?
But that's the only one. Well, we care about 10 to the minus 10 because it's much less than 1. You don't have to care, okay? This is, I can't force you to care, but it's an opportunity, okay? And yeah, I would love to understand why the electron mass is so unnaturally small. I mean, in the precise sense that it's connected in the standard model with the Ikawa coupling, that's about 1 in a million, 10 to the minus 6. And if I had a good idea about that, I'd be happy to tell you about it, but I don't, and as far as I know, nobody does have a good idea about this. So you pursue these clues, and some of them turn out to be fruitful, and some of them don't. But an example of one that turned out to be very fruitful was the equivalence principle. People found this unnatural match between gravitational and inertial mass. Another was parity violation, really, if you think about it. People found that parity violation was only in the weak interactions, so it was kind of unnatural, but unraveling that led to a very rich and insightful story. So,
Maybe you should say something about this Axion workshop coming up, which you mentioned.
well, Sebastian here Sebastian Baum is the hero of this, so maybe could you say a few words about what's happening?
So this is a workshop mainly focused on axion dark matter. Right? Both the theory behind it and also the experiments that are currently running and being built that look for axions, and specifically axions if they make up a large fraction of dark matter. So the workshop will be in roughly 10 days. It will start December 5th and run until December 8th. Of course, Frank is one of the organizers. So one of the aims of the workshop is also to get people from here excited in axions. And to facilitate that, on the first day, we will have somewhat more introductory talks. So Monday, December 5th, that are supposed to be accessible for a broad audience of physicists. And also the OPC colloquium will be, on that week, will be on Monday, in fact, instead of Tuesday, and will be a talk by Pierre Sakivi one of the heroes of Axions too, about how to find dark matter axions.
Thank you.
Is there any final question? Doesn't seem to be the case. Then you're all invited
Okay.
to a reception outside the restaurant to celebrate
Okay.
Frank's
Thank you.
coming.
Okay.